In this video, I wanted to attempt to explain the spherical coordinate system. So far we've had the 3D Cartesian, which had components or coordinates x, y, and z, and we've done the cylindrical, which had components s, phi, and z. And so now we want to look at the spherical system, which has components or coordinates r, phi, and theta. So we can begin by drawing our axis, and we have our major axis x, y, and z. And next we want to have a point, and we want to project that point into the xy plane. And if you can recall that we defined s to be the distance from the projected point, from the origin to the projected point in the xy plane, and it makes the angle theta with the x-axis. And we defined r to be the distance from the origin to the point, and it makes an angle with the the z-axis called theta. And so we can sort of start to begin to form some relationships if we recall some of the other coordinate systems. So remember, we could call this, in Cartesian we called this x, y, and z. So it had x, y, and z component. And so this is your x, this is your z. This is your x, this is your y, and this is your z. And we had our s here, and so we can sort of translate this up distance z, and we see that this is also equal to s. And then we can sort of translate this z backward a distance s, or the distance s, and we'll get a z over here. So these are equal, s is equal, s is equal. And you can sort of see this plane that forms here. And this s is perpendicular to the z, so you can sort of see that. And so now we want to begin to derive some relationships between all of these components. So we'll skip down to here. If you can see this little triangle here, we're going to translate it and try to derive some relationships using trig functions. So here we had our r and our theta, and we said that this vertical piece is equal to z, and this horizontal piece is equal to s. So if we use our handy-dandy SOHCAHTOA, we'll see that sine theta is equal to the opposite over the hypotenuse, which is s over r. We'll see that cosine theta is equal to the adjacent over the hypotenuse, which is z over r, and our tangent theta is equal to our opposite over adjacent, which is s over z. And from these relationships we can solve for s, which is a polar coordinate, in terms of spherical coordinates. So s is equivalent to r sine theta, z is r cosine theta, and theta is equal to inverse tangent s over z. So now that we've formed those relationships, we can come here and we see that r, in terms of Cartesian coordinates, is just distance, s squared, y squared, z squared. So we get r is equal to the square root of x squared plus y squared plus z squared. And we've derived these previously, where we said that S is equal to R sine theta, C is equal to R cosine theta, right here, tangent, and cosine. So with those relationships, we have previously defined x in terms of polar coordinates, and so we're just going to bring those relationships in with what we've just defined s as in terms of spherical coordinates. So our s becomes r, I can draw a little bit here just to make it easier. So this s replaces this s, and we're left with r, which you can see sort of here, it's kind of broken up, r sine theta, and we're left with that remaining cosine phi. And we'll do the same thing with our y component. In polar system, we defined y as s sine theta. So we're going to take that s, and we've defined it in spherical terms. So we're going to replace it here, and we'll get r sine theta, and we'll have this remaining phi theta. And that is how we go from Cartesian to spherical. And we use the step in between, the common denominator of a polar. And that is how we understand 3D spherical, Cartesian, cylindrical. So we have to use a little bit of everything to derive these relationships.